Black holes emerge from the dramatic collapse of massive stars, those exceeding 20 solar masses or 3.978 times 10 to the 31st kilograms, after they exhaust their nuclear fuel in a supernova explosion. This collapse compresses matter into a singularity, a point where density reaches infinity and gravity warps space-time beyond human comprehension. Astronomers estimate our Milky Way galaxy contains over 100 million stellar black holes with individual masses ranging from 3 to 20 times the Sun's 1.989 times 10 to the 30 kilograms. But these numbers are just the starting point of their mysteries. Secret 1. Astonishing size variations. Primordial black holes theorized to form in the Big Bang's first microseconds could be as minuscule as 0.000000001 millimeters across, weighing mere micrograms. In stark contrast, supermassive black holes like Sagittarius A star at our galaxy's center span 44 million kilometers, equivalent to 30 times the 384,400 kilometer Earth-Moon distance. The 2025 Event Horizon Telescope update revealed black holes with event horizons stretching an incredible 10 billion kilometers, a scale that redefines our cosmic perspective. Secret 2. Gravity's overwhelming force. A black hole's gravitational pull can reach 10 to the 38th times Earth's modest 9.8 meters per second squared, meaning at just 10 kilometers from a 10 solar mass black hole, you'd endure 10,000 G-forces. This intensity stretches objects into strands through spaghettification within seconds. This gravity also bends light, creating gravitational lensing, with 15 new events documented in 2024, providing indirect glimpses of these invisible behemoths. Secret 3. Extreme temperature duality. Near the event horizon, the boundary where escape velocity hits 300,000 kilometers per second, temperatures plummet to within 0.0000001 degrees Celsius of absolute zero, or minus 273 degrees Celsius. However, the accretion disk, a swirling maelstrom of matter, can blaze at 10 million degrees Celsius due to friction and compression. NASA's Chandra X-ray Observatory has logged over 500 such emissions in the past decade, showcasing this fiery cold paradox. Secret 4. Hawking radiation's gradual erosion. Stephen Hawking's groundbreaking theory suggests black holes aren't eternal. Quantum fluctuations near the event horizon spawn particle-antiparticle pairs, with one falling in and the other escaping, sapping mass at a rate of 10 to the negative 28th power grams per second for a 10 solar mass black hole. Over an astronomical 10 to the 67th years, trillions of times the universe's 13.8 billion year lifespan, it could evaporate entirely. In 2025, the European Space Agency's XMM Newton satellite detected faint Hawking radiation signals from a black hole 1,500 light-years distant. Secret 5. Collision's universe-shaping power. When black holes merge, they release energy equivalent to 3 solar masses, or 5.4 times 10 to the 47th joules, as gravitational waves. Since 2015, the LIGO Observatory has recorded 150 such events, with the most recent on March 10, 2025, unleashing energy sufficient to power Earth for 10 billion years. Computer simulations indicate that 10% of the estimated 2 trillion galaxies in the observable universe bear signs of recent mergers. Secret 6. NASA's 2025 revolution. The Black Hole Imager, a constellation of 12 satellites launched in January 2025, maps event horizons with unprecedented 0.1 microarc-second precision, 100 times sharper than prior instruments. This mission identified 8 intermediate mass black holes, ranging from 100 to 10,000 solar masses in the Andromeda Galaxy, increasing the known count to 16. Secret 7. The event horizon's critical edge. This boundary, where light cannot escape at 300,000 kilometers per second, spans 30 kilometers for a 10 solar mass black hole. The 2025 Event Horizon Telescope expansion, covering 30% more of the sky, detected a 0.01% energy anomaly near one horizon, hinting at undiscovered physics. Secret 8. Quasar's brilliant power source. Quasars, the universe's brightest objects, emit 10 to the power of 40 watts, trillions of times the sun's 3.8 times 10 to the power of 26 watts, and are fueled by supermassive black holes consuming 1 solar mass per year. In 2025, the Hubble Space Telescope discovered 50 new quasars, located 13 billion light-years away, illuminating the early universe's history. Secret 9. Dark matter's hidden alliance. Black holes may harbor 1% of the universe's 27% dark matter content. A 2025 Dark Energy Survey analysis estimates 10 to the 15th power kilograms of dark matter orbiting Sagittarius A star, influencing its 4 million solar mass growth over 10 million years. Secret 10. Energy anomalies at the core. Theoretical models predict a 10 to the power of 19 giga-electron-volts energy spike at the singularity, far beyond the 14 tera-electron-volts limit of current particle accelerators. The 2025 data reveals a 0.001% mass anomaly, sparking debates about wormholes or new particles. Secret 11. Spin and relativistic jets. Black holes can rotate at 0.998 times the speed of light, generating plasma jets extending 1,000 light-years. In 2025, 20 new jets were mapped, each carrying 10 to the 37th watts, enough to outshine 10 billion stars. Secret 12. Accretion disk dynamics. These disks can accumulate 10 to the 25th kilograms of matter yearly, heating to 10 million degrees Celsius and emitting X-rays detectable 100 light-years away. 2025 Chandra data logged 600 new emissions, refining black hole mass estimates. Secret 13. Gravitational wave precision. LIGO's 2025 upgrade detected waves with 0.0001 second accuracy, tracing 10 new mergers with masses totaling 50 solar masses, reshaping galaxy formation models. Secret 14. Historical context. The first black hole image captured in 2019 spanned 40 billion kilometers. By 2025, 10 more images refined our understanding, with resolutions hitting 20 micro-arc seconds. Secret 15. Future horizons. With 10 missions planned by 2030, black holes could reveal 5% more of the universe's 10 to the 53rd kilogram mass. The next decade may uncover 100 new black holes, each with unique signatures. To deepen our exploration, let's consider the theoretical implications. The Kerr solution, describing rotating black holes, suggests a ring singularity with a diameter of 0.1 millimeters for a 10 solar mass black hole, spinning at 0.99 C. This rotation could generate 10 to the 45th power ergs of energy yearly, powering jets visible across 10,000 light-years. In 2025, simulations from the Max Planck Institute modeled 50 such rings, each influencing 1% of a galaxy's 10 to the power of 11 star population. Another angle is the role of magnetic fields. Accretion disks generate fields up to 10 to the power of 8 Tesla, 10 million times Earth's 50 microtesla, channeling 10 to the power of 39 watts into jets. The 2025 Atacama Large Millimeter Array detected 30 new magnetic signatures, linking them to black hole spin rates of 0.995 C. This data suggests 5% of a black hole's 10 to the 36th kilogram mass could be converted to energy over 10 to the 6th years. Let's talk numbers further. The universe's total black hole population might exceed 10 to the power of 9, with 1% being supermassive, totaling 10 to the power of 7 objects. Each supermassive black hole, averaging 10 to the power of 9 solar masses, could influence 10 to the power of 12 stars within a 100 light-year radius. The 2025 Gaia mission mapped 1,000 such influences, refining mass estimates by 0.1%. The cosmic microwave background offers clues too. Black holes may have contributed 0.01% to the 2.725 Kelvin temperature fluctuations detected by the Planck satellite in 2025 with a 0.0001 Kelvin precision. This ties to the 10 to the 22nd giga-electron-volts energy scales theorized for early universe black holes, formed 10 to the negative 35th seconds after the Big Bang. Join Just the Universe for weekly cosmic dives. Subscribe, hit the bell, and next time, exoplanets await. What's your theory on a black hole's core? Comment below. We're excited to read. What powers the stars that light up the night sky, and what happens when they burn out? Welcome to Just the Universe, where we unravel the cosmos's greatest stories. Stars are the universe's engines, born in massive clouds, shining for billions of years and sometimes dying in explosions that outshine entire galaxies. Today we're diving into the epic life cycle of stars, from their fiery births to their dramatic deaths as white dwarfs, neutron stars, or black holes. With jaw-dropping numbers and cosmic insights, we'll explore how stars shape the universe and even create the elements in your body. So let's blast off and follow a star's journey from cradle to grave. Stars begin in nebulae, vast clouds of gas and dust spanning up to 100 light-years across and containing 10,000 to 10 million solar masses of material. The Orion Nebula, 1,344 light-years away, is a stellar nursery birthing 3,000 stars right now. Gravity pulls gas, mostly hydrogen, 73.5% by mass, and helium, 24%, into dense clumps called protostars. As a protostar collapses, its core heats to 18 million degrees Fahrenheit, igniting nuclear fusion. This process, where hydrogen nuclei fuse into helium, releases energy equivalent to 3.8 times 10 to the 26th watts for our sun. Enough to power Earth's grid for 10 billion years. A protostar's birth takes 100,000 to 1 million years, depending on its mass. Low-mass stars like red dwarfs at 0.08 solar masses form slowly, while massive stars up to 100 solar masses collapse faster in just 10,000 years. The James Webb Space Telescope in 2025 imaged 180 protoplanetary disks in the Orion Nebula, each 0.01 light-years wide, showing planets forming alongside stars. Once fusion begins, a star's outward pressure balances gravity, and it enters the main sequence, where it'll spend most of its life shining steadily. Here at Just the Universe, we're passionate about the cosmic stories that shape our skies. If you're loving this stellar journey, hit that like button, subscribe, and turn on notifications for more space adventures. Drop a comment. What's your favorite star or nebula? Let's keep the cosmic convo sparkling. The main sequence is a star's prime, where it fuses hydrogen into helium in its core. Our Sun, a G-type star with a mass of 1.99 times 10 to the power of 30 kilograms, has been on the main sequence for 4.6 billion years and will stay there for another 5.4 billion. Its surface burns at 10,000 degrees Fahrenheit, producing 3.8 times 10 to the 33rd ergs per second, equivalent to 90 billion megatons of TNT. Stars' lifetimes depend on mass. A red dwarf at 0.1 solar masses can shine for 10 trillion years, while a massive O-type star, 20 solar masses, burns out in just 10 million years, fusing hydrogen 10,000 times faster. The Hertzsprung-Russell diagram, which plots 90% of stars, shows main sequence stars range from 0.08 to 100 solar masses and 0.0001 to 1 million times the sun's brightness. In 2025, the Gaia mission mapped 1.8 billion stars, revealing 70% are main sequence, with 50% being red dwarfs. These stars, like Proxima Centauri 4.24 light-years away, are dim but stable, making up 20% of the Milky Way's 100 billion stars. Massive stars, though rare, dominate star-forming regions, with 1% of stars producing 90% of a nebula's light. When a star like our Sun exhausts its core hydrogen, it leaves the main sequence after 10 billion years. Its core contracts, heating to 180 million degrees Fahrenheit, while outer layers expand into a red giant, swelling 100 times its original diameter to 70 million miles, engulfing Mercury and Venus. Betelgeuse, a red supergiant 642 light-years away, is 900 times the Sun's diameter, spanning 800 million miles. Red giants fuse helium into carbon and oxygen, releasing 1,000 times more energy than the Sun's current output. Low to medium mass stars, 0.8 to 8 solar masses, shed their outer layers, forming planetary nebulae like the Ring Nebula, 2,300 light-years away, which spans 1 light-year. The core collapses into a white dwarf the size of Earth, 8,000 miles across, but with 0.6 solar masses so dense a teaspoon weighs 15 tons. White dwarfs cool over trillions of years, with 10 billion in the Milky Way today. In 2025, JWST imaged 50 planetary nebulae, revealing carbon-rich shells that seed galaxies with life's building blocks. If you're hooked on how stars evolve, show some love for Just the Universe. Smash that like button, subscribe, and comment. Would you want to see a red giant or a white dwarf up close? Let's keep exploring the stars. Massive stars, 8 to 100 solar masses, end with a bang, a supernova. When their cores exhaust helium, they fuse heavier elements like silicon and iron in just days. The core, reaching 3 billion degrees Fahrenheit, collapses in 0.1 seconds into a neutron star or black hole, releasing 10 to the 46th joules, 100 times the Sun's lifetime energy output. This explosion outshines a galaxy, reaching 10 billion solar luminosities. Supernova 1987, 168,000 light-years away, peaked at 100 million suns brightness and is still studied in 2025 for its neutrino emissions, with 19 neutrinos detected in 1987. Supernovae come in types. Type 2 for massive stars releasing 10 to the 44th ergs, and Type 1a for white dwarfs in binary systems detonating at 1.4 solar masses. In 2025, the Vera C. Rubin Observatory detected 1,200 supernovae, showing they occur every 100 years per galaxy. These explosions scatter elements like iron, 60% of Earth's core, and gold, 0.01% of Earth's crust, forging 92 natural elements. The Crab Nebula, 6,500 light-years away, is a supernova remnant from 1054 CE, spanning 11 light-years and glowing with 75,000 solar luminosities. Stars don't just die, they shape the universe. Supernovae seed galaxies with heavy elements, producing 10 Earth masses of carbon per event. The Milky Way's 10 to the 24th tons of iron came from billions of supernovae over 13 billion years. Stellar winds from red giants and supernovae enrich nebulae, triggering new star formation. In 2025, the Atacama Large Millimeter Array observed 200 star-forming regions, showing 30% of their mass comes from recycled stellar material. The future holds more discoveries. By 2030, the Nancy Grace Roman Space Telescope will catalog 100 million stars, mapping their life cycles with 1% precision. The Square Kilometer Array will detect 10,000 supernova remnants, revealing how stars seed galaxies. Stars also test physics. White dwarfs confirm quantum mechanics via electron degeneracy, while supernovae probe neutrino oscillations. With 100 billion stars in the Milky Way and 2 trillion galaxies, each star's life cycle is a chapter in the universe's story. From birth in glowing nebulae to explosive deaths as supernovae, stars are the universe's architects, forging the elements that make planets and life possible. Here at Just the Universe, we're thrilled to share their epic journey with you. If you love this dive into stellar evolution, please like this video, subscribe to the channel, and hit the notification bell for more cosmic content. Drop a comment. What's your favorite stage of a star's life, or what star would you love to learn about next? Let's keep unraveling the cosmos together. Until next time, keep shining like the stars. What if you could see the universe as it was just 200 million years after the Big Bang? Or peek into the atmospheres of planets light years away? Welcome to Just the Universe, where we explore the cosmos's greatest mysteries. In 2025, the James Webb Space Telescope, or JWST, is delivering jaw-dropping discoveries that are reshaping astronomy. From galaxies born at the dawn of time to hints of life on distant worlds, JWST's 21-foot golden mirror is unlocking secrets we never thought possible. Today, we're diving into its latest breakthroughs, packed with mind-blowing numbers and cosmic wonders. So let's launch into the universe and see what JWST has found in 2025. The James Webb Space Telescope, launched on December 25, 2021, is NASA's most powerful observatory ever, costing $10 billion and boasting a 21.3-foot wide primary mirror made of 18 gold-coated beryllium segments. Unlike Hubble, which sees mostly visible light, JWST observes in infrared, allowing it to peer through cosmic dust and detect light from objects 13.5 billion light-years away. Light that's been traveling since the universe was just 2% of its current age, 13.8 billion years. Its 4 instruments, including the NIRCam and MIRI, capture images and spectra with a resolution sharp enough to spot a bumblebee on the moon from Earth, metaphorically speaking. JWST orbits the Sun at the L2 Lagrange point, 930,000 miles from Earth, where it stays cool at -370 degrees Fahrenheit to detect faint infrared signals. In its first 3 years, JWST observed over 2,000 celestial targets, producing 1.4 petabytes of data, enough to fill 1,401 terabyte hard drives. By June 2025, it has imaged 700 galaxies, 400 exoplanets, and 1,200 star-forming regions, with 85% of its observations publicly available. These numbers show why JWST is a game-changer, revealing details Hubble could never see, like stars forming inside dusty nebulae or the chemical makeup of alien atmospheres. If you're as thrilled about JWST's discoveries as we are here at Just the Universe, hit that like button, subscribe, and turn on notifications for more cosmic adventures. Drop a comment. What JWST discovery are you most excited about? Let's keep the universe buzzing. One of JWST's biggest feats is spotting galaxies from the universe's infancy. In 2022, its first deep field image, SMACS0723, revealed thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length, some 13.1 billion light-years away. By 2025, JWST's Sears survey has identified 12 galaxies formed just 200 to 400 million years after the Big Bang, when the universe was less than 3% of its current age. The farthest, dubbed Maisie's galaxy, is 13.5 billion light-years away, with a redshift of 11.8, meaning its light is stretched by the universe's expansion to 12 times its original wavelength. These early galaxies are tiny compared to the Milky Way, just 1,000 to 10,000 light-years across. But they're forming stars at a furious rate, up to 100 solar masses per year, 10 times faster than our galaxy. JWST's spectra show they're rich in hydrogen and helium, with traces of oxygen formed in the first star's cores. In March 2025, JWST confirmed a galaxy JADESGSZ140, with a mass of 500 million suns formed when the universe was only 290 million years old. This challenges theories that galaxies took longer to grow, suggesting the early universe was a chaotic star factory. JWST isn't just looking back in time, it's hunting for signs of life on exoplanets. Its infrared spectrometers can analyze starlight passing through a planet's atmosphere, revealing its chemical makeup. By June 2025, JWST has studied 65 exoplanet atmospheres, detecting water vapor on 40, carbon dioxide on 25, and methane on 15. A standout is WASP-39b, a hot Jupiter 700 light-years away, where JWST confirmed sulfur dioxide in 2023, a molecule formed by starlight-driven chemistry. In January 2025, JWST found water vapor and possible dimethyl sulfide, a potential biosignature, on K218b, a super-Earth 120 light-years away, sparking debate about life 2.6 times Earth size. Another 2025 breakthrough is LHS 1140b, 48 light-years away, where JWST detected an ocean covering 25% of its surface, with depths up to 7 miles. This planet, 1.7 times Earth's diameter, orbits in its star's habitable zone, receiving 90% of Earth's solar energy. Its atmosphere, rich in nitrogen and oxygen, hints at habitability, though more data is needed. JWST's exoplanet observations cover planets from 0.8 to 11 times Earth's mass, with 20% showing signs of stable atmospheres conducive to liquid water. If you're loving these cosmic revelations, show some support for Just the Universe. Smash that like button, subscribe, and comment. Do you think JWST will find proof of alien life? Let's keep exploring the stars together. JWST is also a master at uncovering how stars are born. Its infrared vision pierces dusty clouds where stars form, revealing details down to 10 astronomical units about the distance from Earth to Saturn. In 2024, JWST imaged the Carina Nebula, 7,600 light-years away, showing 3,000 protostars embedded in gas pillars 10 light-years tall. These baby stars, some just 100,000 years old, range from 0.1 to 50 solar masses. By 2025, JWST has mapped 15 star-forming regions identifying 12,000 protostars and 500 disks where planets may form. A key discovery is in the Orion Nebula, 1,344 light-years away, where JWST spotted 180 proplids, protoplanetary disks glowing around young stars. These disks, 0.01 to 0.1 light-years wide, contain enough material to form 10 to 100 Earth-like planets. JWST's spectra show they're rich in silicates and water ice, the building blocks of rocky worlds. In April 2025, JWST revealed a jet from a protostar in NGC 1333, stretching 2 light-years and moving at 223,000 miles per hour, sculpting the nebula like a cosmic sandblaster. These findings show how stars and planets emerge from chaos, shaping galaxies over billions of years. JWST's mission is far from over. With a planned lifespan to 2031, it has fuel for at least 20 years thanks to a precise launch that saved 80% of its propellant. In 2026, JWST will begin the Cosmos Web Survey, mapping 1 million galaxies across 0.6 square degrees of sky, 10 times larger than its 2022 deep field. It's also set to study 100 more exoplanets, focusing on rocky worlds and habitable zones. By 2028, JWST will team up with the Nancy Grace Roman Space Telescope, launching in 2027 to survey 10 million stars for exoplanets, potentially finding 100,000 new worlds. Theoretically, JWST could detect biosignatures like oxygen or phosphine on nearby exoplanets, with a 70% chance of identifying a habitable world by 2030, according to some astronomers. Its data also supports dark matter studies, with 2025 observations of galaxy clusters showing 27% of their mass is dark matter, bending light from background galaxies. With 100,000 hours of observation time left, JWST will keep pushing the boundaries of what we believe is possible. The James Webb Space Telescope is our window to the universe's past, present, and future. From ancient galaxies to potential alien oceans, its 2025 discoveries are bringing us closer to answering life's biggest questions. Here at Just the Universe, we're passionate about sharing these cosmic breakthroughs with you. If you love this journey through JWST's findings, please like this video, subscribe to the channel, and hit the notification bell for more stellar content. Drop a comment. What's your favorite JWST discovery, or what do you hope it finds next? Let's keep exploring the cosmos together. Until next time, keep gazing at the stars. What if there's another Earth out there waiting to be found? Could a distant planet hold the key to answering one of humanity's biggest questions? Are we alone in the universe? Welcome to Just the Universe, where we explore the mind-blowing mysteries of the cosmos. Today, we're diving into the search for habitable exoplanets, worlds beyond our solar system that might just support life. From NASA's groundbreaking missions to the latest discoveries in 2025, we'll uncover the science, the stats, and the sheer wonder of these alien worlds. So buckle up and let's embark on a cosmic journey to find the next Earth. What makes a planet habitable? To understand the search for habitable exoplanets, we first need to know what makes a planet capable of supporting life as we know it. Scientists focus on a region around a star called the habitable zone, or the Goldilocks zone. This is the sweet spot where temperatures are just right, not too hot, not too cold, for liquid water to exist on a planet's surface. Water is crucial because every form of life we know depends on it. But the habitable zone isn't one size fits all. For a star like our Sun, the zone stretches from about 0.95 to 1.37 astronomical units, or AU, where 1 AU is the distance from Earth to the Sun, roughly 93 million miles. For cooler, smaller stars like red dwarfs, the habitable zone is much closer, sometimes as tight as 0.1 to 0.4 astronomical units. Size matters too. A habitable exoplanet is typically rocky, like Earth, with a diameter between 0.8 and 1.6 times Earth's, about 6,400 to 20,000 miles across. Too small, and the planet might lack the gravity to hold an atmosphere. Too big, and it could become a gas giant like Jupiter with no solid surface. Then there's the atmosphere itself. It needs to trap enough heat to keep water liquid, but not so much that the planet turns into a scorching Venus, where surface temperatures hit 870 degrees Fahrenheit. Scientists also look for biosignatures, gases like oxygen or methane, that could hint at life. In 2024, the James Webb Space Telescope detected potential traces of dimethyl sulfide, a gas produced by marine life on Earth, in the atmosphere of exoplanet K218b, sparking global excitement. Here at Just the Universe, we love diving into the numbers and discoveries that shape our understanding of the cosmos. If you're as fascinated by these alien worlds as we are, hit that like button, subscribe, and turn on notifications for more space adventures. Drop a comment below. Do you think we'll find a habitable exoplanet in the next decade? Let's keep the cosmic conversation going. NASA's exoplanet hunters. The hunt for exoplanets kicked into high gear in the 1990s, and since then we've confirmed over 5,800 exoplanets as of June 2025, with thousands more candidates awaiting verification. NASA's Kepler Space Telescope, launched in 2009, was a game changer. Over its 9-year mission, it discovered 2,662 exoplanets by watching for tiny dips in starlight as planets passed in front of their stars, a method called the transit technique. Kepler stared at a patch of sky containing 150,000 stars, covering just 0.25% of the Milky Way, yet found planets ranging from scorching hot Jupiters to Earth-sized worlds in habitable zones. Its successor, TESS, the Transiting Exoplanet Survey satellite, launched in 2018, has added over 400 confirmed exoplanets to the tally, scanning 85% of the sky for nearby stars within 300 light-years. But finding a planet is only half the battle. To know if it's habitable, we need to study its atmosphere. That's where the James Webb Space Telescope, launched in 2021, comes in. Webb's infrared vision can peer through the atmospheres of distant worlds, identifying gases like water vapor, carbon dioxide, and methane. In 2023, Webb made headlines by confirming water vapor in the atmosphere of WASP-96b, a gas giant 1,150 light-years away. By 2025, Webb has analyzed over 50 exoplanet atmospheres, with 12 showing potential signs of habitability. These numbers are staggering. Each discovery brings us closer to finding a world that could host life. TRAPPIST-1, a cosmic jackpot. One of the most exciting discoveries in exoplanet research is the TRAPPIST-1 system, located just 40 light-years from Earth. In 2017, astronomers announced that this cool red dwarf star hosts 7 Earth-sized planets, 3 of which, TRAPPIST-1, Ia, F, and G, lie in the habitable zone. These planets are so close to their star that their orbits range from 1.5 to 19 days, compared to Earth's 365-day orbit. But because TRAPPIST-1 is only 8% as massive as our Sun, its habitable zone is cozy, with planets receiving just the right amount of heat. Each TRAPPIST-1 planet is rocky and roughly Earth-sized, with diameters between 9,100 and 13,600 miles. Scientists estimate that TRAPPIST-1e, the most Earth-like of the bunch, could have surface temperatures between 32 and 77 degrees Fahrenheit, perfect for liquid water. In 2024, Webb observed TRAPPIST-1e and detected signs of an atmosphere containing nitrogen and oxygen, though more data is needed to confirm. The system's planets are also tidally locked, meaning one side always faces the star, creating a permanent day and night side. This could lead to extreme weather patterns with winds redistributing heat across the planet. The TRAPPIST-1 system is a cosmic jackpot because it offers multiple chances to study potentially habitable worlds in one place. With 7 planets, it's like rolling the dice 7 times in the search for life. If you're loving this deep dive into exoplanets, show some support for Just the Universe. Hit that like button, subscribe, and let us know in the comments. Which TRAPPIST-1 planet do you think is most likely to host life? James Webb's 2025 discoveries. As of 2025, the James Webb Space Telescope is rewriting what we thought was possible in exoplanet research. Its 21-foot-wide mirror and cutting-edge spectrographs allow it to analyze light from planets as small as Earth, even at distances of hundreds of light years. In January 2025, Webb made a stunning discovery. An Earth-sized exoplanet TOI 700e, located 100 light-years away, has a thick atmosphere with water vapor and possible biosignatures. TOI 700e orbits a red dwarf star and receives 95% of the energy Earth gets from the Sun, making it a prime candidate for habitability. Webb's data also revealed that TOI 700e has a day-night cycle lasting 28 Earth days and a surface gravity 0.9 times Earth's. Its star, TOI 700, is stable, unlike many red dwarfs that flare violently, which bodes well for long-term habitability. Another 2025 breakthrough came with LHS 1140b, a super-Earth 48 light-years away. Webb confirmed it has an ocean covering 20% of its surface, with depths up to 6 miles. These discoveries aren't just numbers, they're stepping stones toward answering whether life exists elsewhere. The future of exoplanet exploration. So what's next? The search for habitable exoplanets is accelerating. NASA's upcoming Nancy Grace Roman Space Telescope, set to launch in 2027, will survey millions of stars, potentially discovering 100,000 new exoplanets. The European Space Agency's ARIEL mission, planned for 2029, will study 1,000 exoplanet atmospheres in unprecedented detail. Meanwhile, ground-based observatories like the extremely large telescope in Chile with its 130-foot mirror will image Earth-like planets directly by 2030. Statistically, the odds are in our favor. The Milky Way contains an estimated 100 billion stars, with at least 20% hosting rocky planets in their habitable zones. That's 20 billion potential Earths. If even 0.1% of those have life, we're talking about 20 million life-bearing worlds. The question isn't if we'll find a habitable exoplanet, it's when. Some experts predict we'll detect definitive biosignatures by 2035, while others think it could happen as early as 2028. The search for habitable exoplanets is one of the most thrilling quests in human history. Each discovery brings us closer to answering whether we're alone in the universe. Here at Just the Universe, we're passionate about sharing these cosmic breakthroughs with you. If you enjoyed this journey through alien worlds, please like this video, subscribe to the channel, and hit the notification bell so you never miss an update. Drop a comment below. Do you think we'll find life on an exoplanet in your lifetime? Let's keep exploring the universe together. Until next time, keep looking up. Galaxy. What's the densest thing you can imagine? A mountain? A planet? Try a neutron star, a cosmic object so dense that a single teaspoon of its material weighs as much as Mount Everest, about 10 billion tons. Welcome to Just the Universe, where we unravel the wildest mysteries of the cosmos. Today, we're diving into the incredible world of neutron stars, the remnants of massive stars that pack mind-blowing physics into a tiny space. From their crushing gravity to their role in creating the gold in your jewelry, we'll explore the science, the numbers, and the cosmic wonders of these stellar powerhouses. So let's blast off and discover what makes neutron stars the universe's ultimate heavyweights. Neutron stars are born from the violent deaths of massive stars, those at least 8 times the mass of our Sun, or about 2.6 million Earths. When these stars run out of fuel, their cores collapse in a supernova explosion, releasing as much energy in a few seconds as our Sun will emit in its entire 10 billion year lifetime. That's 10 to the 44th power joules, enough to outshine an entire galaxy. What's left behind is a neutron star, a super-dense core about 12 to 15 miles across, roughly the size of a city like Los Angeles, but containing 1.4 to 2 times the Sun's mass, or 4.6 times the Sun's mass, 10 to the power of 30 pounds. Inside a neutron star, gravity is so intense that protons and electrons get squashed together to form neutrons, creating a material 10 trillion times denser than lead. The surface gravity is 200 billion times stronger than Earth's, meaning a 150-pound person would weigh 30 trillion pounds there. The crust, just half a mile thick, is made of iron nuclei so tightly packed it's 10 billion times stronger than steel. Beneath it lies a bizarre neutron soup and possibly exotic states of matter like quark gluon plasma, which we can't replicate on Earth. These stars spin insanely fast, some up to 700 times per second, because the collapsing star conserves angular momentum, like a figure skater pulling in their arms. Here at Just the Universe, we're obsessed with the numbers and discoveries that light up the cosmos. If you're geeking out over neutron stars as much as we are, smash that like button, subscribe, and turn on notifications for more space adventures. Drop a comment. Do you think neutron stars could reveal new laws of physics? Let's keep the cosmic convo going. Some neutron stars are even wilder. They're pulsars, beaming radiation like cosmic lighthouses. Pulsars form when a neutron star's magnetic field, amplified during the collapse to 10 to the 12th times Earth's field, funnels charged particles into tight beams at its poles. As the star spins, these beams sweep across space, and if they point toward Earth, we detect them as regular pulses of radio waves, X-rays, or even gamma rays. The first pulsar, discovered in 1967 by Jocelyn Bell Burnell, pulsed 1.33 times per second, earning the nickname LGM-1 for Little Green Men because scientists briefly thought it might be an alien signal. Today, we've cataloged over 3,000 pulsars with periods ranging from 1.4 milliseconds to 8.5 seconds. The fastest, PSRJ 1748-2446A, spins 716 times per second, its surface moving at 24% the speed of light, or 161 million miles per hour. Pulsars are so precise that their pulses rival atomic clocks, losing less than a nanosecond per year. This makes them cosmic timekeepers used to test Einstein's theory of general relativity. In 2017, the Hulse-Taylor pulsar, PSRB 1913+16, confirmed gravitational wave emission, earning a Nobel Prize. By 2025, Pulsar timing arrays like nanograv have detected a hum of low-frequency gravitational waves, likely from merging supermassive black holes using 68 pulsars across the Milky Way. To unlock neutron star secrets, NASA launched the NICER telescope in 2017, mounted on the International Space Station. NICER, or Neutron Star Interior Composition Explorer, studies X-ray emissions to measure neutron star sizes and masses with unprecedented precision. In 2023, NICER mapped the surface of pulsar J0030 plus 0451, revealing hotspots just 330 feet across, despite the star being 1,000 light-years away. This map showed the pulsar is 15.8 miles in diameter and has a mass 1.4 times the Sun's, refining models of neutron star interiors. In 2025, NICER made a breakthrough by measuring the radius of PSR J0740 plus 6620, the most massive known neutron star at 2.07 solar masses. Its diameter, just 13.7 miles, suggesting neutron stars can't get much denser before collapsing into black holes. NICER's data also hints at pasta phases in neutron star cores, structures like sheets or tubes of nuclear matter named for their resemblance to lasagna or spaghetti. These discoveries help physicists test the equation of state, which describes how matter behaves at densities 10 to the power of 15 grams per cubic centimeter, conditions we can't recreate in labs. If you're loving this deep dive into neutron stars, show some love for Just the Universe. Hit that like button, subscribe, and let us know in the comments. What's the coolest neutron star fact you've learned so far? Let's keep exploring the universe together. Neutron stars don't just sit there looking dense. They shape the universe's chemistry. When two neutron stars collide, they unleash a kilonova, a blast 1,000 times brighter than a nova but fainter than a supernova. These collisions produce heavy elements like gold, silver, and uranium through rapid neutron capture, or the R process. In 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron star merger 130 million light-years away. GW 170817. Telescopes saw a kilonova glow, confirming it produced 16,000 Earths worth of heavy elements, including 10 Earths worth of gold valued at 10 to the power of 27 if you could mine it. Each kilonova contributes to the cosmic supply of elements. The Milky Way's gold, estimated at 10 to the 24 tons, likely came from neutron star mergers over billions of years. By 2025, astronomers have detected 12 kilonova events, suggesting mergers happen every 10,000 to 100,000 years per galaxy. These collisions also emit short gamma-ray bursts, lasting less than 2 seconds but releasing 10 to the power of 50 ergs of energy, enough to power our sun for 10 billion years. Neutron stars, then, aren't just cosmic oddities. They're factories for the stuff that makes planets, jewelry, and even us. What's next for neutron star science? By 2030, the Square Kilometre Array, a radio telescope spanning South Africa and Australia, will discover 10,000 new pulsars, tripling our current catalog. This will refine gravitational wave detection and test theories beyond Einstein's relativity. NASA's proposed STROBE-X mission, slated for 2032, will study X-ray emissions from neutron stars at 100 times NICER's sensitivity, probing their core's exotic matter. Meanwhile, the Event Horizon Telescope, which imaged a black hole in 2019, aims to capture a neutron star's surface by 2035, revealing details as small as 1 mile across. Theoretically, neutron stars could unlock new physics. Some scientists speculate they host strange matter, a state where quarks are unbound, potentially converting normal matter into more strange matter. Others propose neutron stars might form axion stars if dark matter particles called axions exist. With 100 million neutron stars estimated in the Milky Way, 1% of its stellar population, each one is a natural laboratory for extreme physics. Neutron stars are cosmic marvels, packing the mass of a star into a city-sized sphere, spinning at dizzying speeds and forging the universe's heaviest elements. From pulsars to colonovae, they challenge our understanding of physics and light up the cosmos in ways we're just beginning to grasp. Here at Just the Universe, we're thrilled to share these discoveries with you. If you enjoyed this cosmic journey, please like this video, subscribe to the channel, and hit the notification bell for more stellar content. Drop a comment. Do you think neutron stars hold the key to new physics? Let's keep the universe's mysteries unfolding together. Until next time, keep staring at the stars. What if a quarter of the universe is made of something we can't see, touch, or detect directly? Sounds like science fiction, but it's real. And it's called dark matter. Welcome to Just the Universe, where we dive into the cosmos's biggest mysteries. Dark matter is the invisible force that holds galaxies together, shapes the universe's structure, and challenges everything we know about physics. In 2025, scientists are closer than ever to cracking its secrets. Today, we'll unpack what dark matter is, how it impacts the cosmos, and the latest breakthroughs, with plenty of mind-blowing numbers to fuel your cosmic curiosity. So let's journey into the invisible universe and uncover the enigma of dark matter. Dark matter is one of the universe's greatest puzzles. It doesn't emit, absorb, or reflect light, making it invisible to telescopes, yet it accounts for 27% of the universe's mass energy, compared to just 5% for normal matter like stars and planets. That's 2.4 times 10 to the 55th power grams of dark matter across the cosmos. Scientists first suspected its existence in the 1930s when Fritz Zwicky noticed that galaxies in the Coma cluster moved too fast, up to 1 million miles per hour, to be held together by visible matter alone. In the 1970s, Vera Rubin's observations of galaxy rotation curves showed stars at a galaxy's edge orbit at the same speed as those near the center, defying Newton's laws unless an invisible mass was at play. Dark matter's gravity binds galaxies, preventing them from flying apart. The Milky Way, for example, contains 200 billion solar masses of dark matter, 10 times more than its visible mass. It's thought to form a halo around galaxies extending 600,000 light-years in diameter, 6 times the Milky Way's visible disk. But what is it? The leading theory suggests dark matter is made of weakly interacting massive particles, or WIMPs, with masses 10 to 100 times a proton's, roughly 1.7 times 10 to the negative 24 grams. Another candidate is axions, ultralight particles 10 to the power of 10 times lighter than an electron. Whatever it is, dark matter doesn't interact with light or normal matter except through gravity, making it a cosmic ghost. Here at Just the Universe, we're obsessed with unraveling the cosmos's secrets, and dark matter is a big one. If you're as fascinated by this invisible force as we are, hit that like button, subscribe, and turn on notifications for more space adventures. Drop a comment. Do you think dark matter is a particle or something totally new? Let's keep the cosmic conversation going. Dark matter's gravity is the scaffolding of the universe. Without it, galaxies wouldn't exist. After the Big Bang 13.8 billion years ago, dark matter clumped under its own gravity, forming dense pockets that attracted normal matter to create the first stars and galaxies within 200 million years. Simulations show dark matter forms a cosmic web, with filaments spanning millions of light years, connecting galaxy clusters that contain up to 1,000 galaxies each. The Virgo cluster, 54 million light-years away, has a dark matter mass of 10 to the 15th power solar masses, bending light from distant galaxies in a process called gravitational lensing. Gravitational lensing is dark matter's calling card. In 2023, the James Webb Space Telescope imaged the Abell 2744 cluster, revealing arcs of light from galaxies 12 billion light-years away, distorted by dark matter's gravity. These arcs stretch across 0.1 degrees of sky, equivalent to a dime seen from 20 miles away. Dark matter also affects galaxy rotation. The Milky Way's outer stars orbit at 560,000 miles per hour, requiring a dark matter halo 1.9 times more massive than its stars and gas. In 2025, the Euclid telescope mapped 10 million galaxies, showing dark matter's web influences 70% of their positions, confirming its role in cosmic architecture. Scientists are racing to detect dark matter directly, and 2025 is a pivotal year. Underground experiments like Lux Zeppelin in South Dakota use 10 tons of liquid xenon to catch WIMPs colliding with atoms. In March 2025, Lux Zeppelin narrowed WIMP masses to 10 to 50 GeV, giga-electron volts, ruling out heavier candidates. That's like finding a needle in a haystack, as WIMPs interact 10 to the power of 40 times weaker than normal particles. Meanwhile, the ADMX experiment in Washington hunts axions, detecting signals as faint as 10 to the negative 22nd watts, equivalent to a candle's light seen from Pluto. Another approach watches the sky. Dark matter particles might annihilate in galaxy centers, producing gamma rays. In 2024, the Fermi Gamma Ray Space Telescope detected a 3.5 GeV signal from the Milky Way's core, hinting at WIMP annihilation, though it's not conclusive. Collider experiments like the Large Hadron Collider smash protons at 13.6 tera-electron volts to create dark matter particles, but no confirmed detections by June 2025. Indirect evidence keeps piling up. The Bullet Cluster, 3.7 billion light-years away, shows dark matter separating from normal matter during a collision, mapped by lensing effects covering 2.5 square degrees. If you're hooked on the hunt for dark matter, show some love for just the universe. Smash that like button, subscribe, and comment. What experiment do you think will crack dark matter first? Let's keep exploring the invisible cosmos. Dark matter's mystery gets even wilder when you compare it to dark energy, which makes up 68% of the universe's mass energy. While dark matter pulls things together with gravity, dark energy pushes the universe apart, driving its accelerating expansion since 5 billion years ago. In 2025, the Dark Energy Spectroscopic Instrument, DESI, mapped 40 million galaxies, showing dark energy's strength is constant, with a density of 6.7 times 10 to the negative 30 grams per cubic centimeter. That's like 1 proton in a cubic meter, yet it dominates the cosmos. Dark matter and dark energy together make up 95% of the universe, leaving just 5% for everything we see: stars, planets, us. Dark matter's effects are local, shaping galaxies, while dark energy acts on cosmic scales, stretching space at 73 kilometers per second per megaparsec, 3.26 million light-years. If dark matter is particles, dark energy might be a field or a cosmological constant, as Einstein proposed. In 2025, JWST's lensing data suggests dark matter halos amplify dark energy's effects in clusters, hinting at a deeper connection. Understanding both could rewrite physics, potentially unifying gravity with quantum mechanics. The hunt for dark matter is heating up. By 2030, the next generation xenon NT experiment will use 50 tons of xenon, 5 times more sensitive than Eluk's Zeppelin, probing WIMP masses down to 1 GeV. The Square Kilometer Array, launching in 2028, will map 1 billion galaxies, refining dark matter's cosmic web to 1% precision. Space missions like NASA's SphereX, set for 2026, will scan the entire sky in infrared, searching for dark matter annihilation signals across 10 to the power of 9 cubic light years. If axions are dark matter, the light trough experiment could detect them by 2032, converting their fields into microwave signals. Theoretically, dark matter could be more exotic: sterile neutrinos, primordial black holes, or even defects in space-time called cosmic strings. With 100 billion galaxies in the observable universe, each hosting 10 to the power of 11 to 10 to the power of 11 solar masses of dark matter, the stakes are high. Some predict a detection by 2035 with a 60% chance of identifying WIMPs or axions. If not, alternative theories like modified Newtonian dynamics or MOND might gain traction, challenging gravity's laws. Dark matter is the invisible glue of the universe, shaping galaxies, bending light, and pushing the boundaries of physics. From underground labs to cosmic surveys, 2025 is bringing us closer to unveiling its secrets. Here at Just the Universe, we're thrilled to share these cosmic mysteries with you. If you loved this dive into the invisible, please like this video, subscribe to the channel, and hit the notification bell for more stellar content. Drop a comment. Do you think we'll solve the dark matter puzzle in your lifetime? Let's keep unraveling the cosmos together. Until next time, keep chasing the invisible stars.